Hello, everybody. This is the some problem solutions for the course MATH2099 at University of New South Wales. In this video, we will work on the orthogonal complements of a vector space and the projections to that vector space and to their orthogonal complement. Yes, okay. Let's remind ourselves what was the orthogonal complement of a vector space. So W is a subspace of a vector space. And W perp is defined as all the vectors in V, in the bigger vector space, such that the inner product between V and W has to be 0 for all W in W. So this is a very strong requirement, as you realize that these V's are the ones that are for all vectors in W, it will be 0 when you multiply with the inner product. So this is a very strong requirement. The best way to think about, visualize, or understand conceptually is an example, in the three-dimensional space. And if you think about the subspace of a three-dimensional space, R3 is like a plane, and the vectors which will be the 0 when you multiply with every vector on the plane will be the normal vectors. So as we know, we have infinitely many normal vectors, normal to the plane. So that runs through the everything except that plane. And it gives you as a sum, it gives you the whole R3. So any vector which is not on that plane in R3 will be the vector in the complement space. So the best way to find the basis for the complement place in this example will be the normal of the plane, because the normal of the plane will give you everything in the outside of that plane in R3. So this is a basic example for complementary, if you conceptually to understand it. And as we know, orthogonal bases or orthonormal bases are really important. And we are going to use the concept of orthonormal bases when we are working on the projections of a vector in V on the vector space of W on the vectors or the vector space of W perp. And this is a vector space as well. What is the advantage of this? Because every vector in V can be written as a sum of vector in one of them in W and one of them in W perp. As you realize that every vector in R3 can be written as a sum of a vector in the plane and something not in the vector of the plane. So it will be like a projection on the plane and the projections to the normal of the plane. Okay, so in order to be able to calculate the projection of a vector space, projection of a vector on a vector space W and orthogonal complement of W, we need to have an orthonormal basis. If you don't have an orthonormal basis, you are required to find orthonormal basis by using the Gram-Schmidt method that we've done last week. Okay, so assume that the B is a basis, orthonormal basis, B1, B2, Bm for some dimension. What it means, orthonormal, just reminding ourselves, any two, if you take any two of those vectors, and you multiply them, then you will get 0. If you multiply its inner product, scalar multiplications, or the dot product of the vector by itself will give you 1. This is similar to the standard basis of R3 that like E1 will give you always 1, E1, E2 will give you always 0. So you can think of the orthonormal basis. The best example should be kept in mind is the standard basis of the Euclidean space, of the Riemann space. Okay, this is the projection. This is a formula for the projection of any vector on V. This should be on V, not W. This is okay. I'm repeating myself. This is on W, but here the vector X is any vector in V. Okay, for the projection, we will just, this is the dot product. We are going to multiply this vector X by every orthonormal basis element. And this will give the coefficients of the linear span with respect to B1, B2, Bm. So this is a scalar, right? Because this is a dot product. This is a vector. This is another vector. So when you multiply it with the dot product, this is the real number, as you realize this is. And this is the vector B1. So this is a multiple of B1. You're shrinking or you are stretching of the vector B1. And similarly, those ones, and similarly that one. This will give us a formula for the projection of any vector X on the vector space W. The projection of this can be done for W. Anyway, let me put it that way first. The projection of any vector on the orthogonal complement will be just when you subtract X minus the projection of W, you will be able to obtain that one. This is coming from basically the definition of orthogonal spaces, because orthogonal space and the orthogonal complement of the space gives you the whole vector space V, or whole vector space of R3 in this example. And this is a unique combination. So the intersection between W and the W complement will be just a zero vector. And so they are orthogonal. It's really they are orthogonal. It means that the sum of projection of X and the sum of the projection of this gives you the X. This is what it means, right? That's what I'm trying to say here. Let me put it that way. The projection of Wx and the projection of W perp X gives you X. This is the key point here. And in particular, this is a particular perpendicular to W, and so is in W perp, which is the orthogonal complement of W. This is the one way to calculate the projection of X on W and X on W prime. And another way of doing it is by using a matrix theory. So weaving those things as a matrix, whatever it works. So you establish the matrix Q such that the column matrix or column of this matrix will be your orthonormal basis. That's B1, B2, B3, Bm. And this is the transpose. You take the transpose of this matrix and multiply it, and that will give you the projection transformation. So for any vector, if you evaluate it, so X, Q transpose QX will give you automatically this calculations. It is exactly the equivalent to it. This is a matrix form of the transformations of the projection of X on W. That's another way of doing it. So in any question, you can choose this method or this method, whatever works better. With the matrix method, you can use it, or you can do your calculation, check your calculation by using any computer aid. You can use a MATLAB, you can use Wolfram, Mathematica, whatever that you're using. You can enter this matrix and calculate the transpose and multiply, and that will, in that way, you can check your calculation, manual calculation that you can get. Usually, manually, when you are doing it, this is easier. This is easier when you're using the computer. Okay, so the question 61, we have vector V, we have A1, A2, so the R space in R3, and W is the subspace spanned by A1, A2. Now let's look at this vector A1 and A2. They are not multiple each others. So since you have two vectors and they are not multiple each others, you can immediately say that they are linearly independent. So the vector A1 and a vector A2 are linearly independent. So spanning of these linearly independent vectors gives you a two-dimensional subspace. So W is a two-dimensional subspace in R3, right? This is what we see when we are reading this question immediately. The question is, find the projections of V on W and find how we write V as a sum of W1, W2, such that W1 will be in W and W2 will be in the orthogonal complement of W. And then we would like to find the shortest distance from a point to W. And we would like to find the reflections of V in the plane W. So this is the question, and let's solve it. Now, first, we have the linearly independent two vectors. But in order to be able to apply the projection formula here, we need to find orthonormal bases, right? This is the key point. So let's have a look whether these two vectors gives us an orthonormal basis. In order to be able to see that, check that, we need to look at the dot product. This is the table for the dot product of these two vectors. So this A1 by itself will be 2 times 2 is 4 plus 5 plus 4. 4 plus 4 is 8 plus 1 is 9. So this is 9. It is the dot product A1 by itself. If you do the dot product with A1 and A2, that will be 2 times 3 is 6. 1 times 1 is 1. 6 plus 1 is 7. That will be 0. So this is 0. And for A2 by itself, we will have the dot product A2 by A2. That will be 3 times 3 plus 1. That is 10. Once you find out this area, you don't need to find out this area at all. So this is really irrelevant for you. This is really irrelevant for you because as we know that the dot product is a commutative, that will be A1, A2 is really equal to A2, A1. So once you find out A1 times A2, you will just put this number into here. You don't need to calculate it. This is always the case when you're doing the dot product table of the vectors, because dot products is commutative. Yeah, I prefer to do this table because it is very clear to see what's going on rather than doing the bits and pieces in a corner. It gives you the result immediately. It is very practical and efficient. I strongly advise to use the table for the dot products to see what's going on. So as we see, this is not an orthonormal, even not orthogonal, because we want this times this. For an orthogonal one, for example, this could be anything, but when we multiplied A1 to A2, this should be 0. This is what we want. We want these numbers 1, 1, and these numbers 0, 0 for the orthonormal basis. For orthogonal basis, we want this number could be anything, this number could be anything, but we really require this one is 0, this one is 0. So orthogonal bases are the bases with the vectors are orthogonal together, each other, but the length could be anything. So these numbers are related with the length. The square root of this number is the length of A1. Square root of this number will be the length of A2. As we know that length of AI is the square of AI dot AI for each those vectors. So since this one is not 1, this is not a unit vector, the length is not 1, and this is not 1, it is not a unit vector. So even this is not an orthogonal and it's clearly not an orthonormal. As we know, the Gram-Schmidt method would tell us how to find out the orthonormal basis for given any set of linearly independent vectors. So we are going to apply the Gram-Schmidt method. This is the Gram-Schmidt method here. This is the formula for Gram-Schmidt method. We know that this is from the last week calculations. The method says that to take, we construct the V1, V2, V2, V3s first, and this is the set how we find out that calculations, how we find out those vectors. And these V1, V2 vectors will give us orthogonal set of the bases, and then we will find orthonormal basis by normalizing those vectors, making it the length is 1. You can make any vector of length 1 by just dividing all those vectors into their length. Okay, so the Gram-Schmidt method says that the first vector V1 is equal to A1, and the V2 is calculated by A2 minus projection of V1, A2. In this case, the projection of the vector to a vector. And in our question, we are interested of the projection of a vector on a vector space. That's a different problem. Calculating this projection, so there's a projection formula. So V1, A2, V1, V1, but V1 is A1. So this is why I'm doing the A1 here. A1, A2, A1, A1, and I can use the table that I've constructed here. This is 7/9 A1. And V2 will be A2. This is A2 minus this vector, which is 7/9. A1 is 2, 1, 2. As you realize, I'm just doing the calculations. You can check it later on. So VT can be found with this vector. So I have V1, which is A1, this vector, and I have V2, which is this vector. And we know that the length of A1 is not 1 because this is 9. Square root of 9 is 3. So the length of a V1 or A1 is 3. So it is not 1. So then we would like to find out this V1 and V2 are the orthogonal bases. Now we would like to normalize it. So this is the process. It's called normalization. This is normalizing. We are normalizing. What we are saying is that when we are normalizing, we are dividing each vector to its length, right? The length of V1 is 3, so this is V1, which is A1 basically. So dividing as 1, so the length of this vector is just 1. If you multiply this by itself, you will find out that U1 times U1 is 1. Yeah. If you looked at the, let me use this one. If you looked at the length of U1, which is the square root of 1/3, 1/3, 212, dot product 212, that will give you 1. That's what I'm trying to say. And it is the same thing for any, because when you take the length of this vector, so the length will be the denominator length, and the numerator length is the same, so it will always be 1. So the length of U1 will be 1. So U1 is a unit vector. So we are making the vector V1, normalizing it. We are making that vector as a unit vector, making the length 1. And similarly for U2, we'll be calculating the length of V2 and dividing by the vector V2. This is the vector V2, and that is the length of V2. That's root of multiplication of this by itself as a dot product, and the square root of it as a definition of the length. You find the root 41 divided by 3. And this number, right, this one is V2. 1 over root 41 over 3 is the length of V2. And then compute this number will give you this vector. So U1 is this vector, U2 is this vector, and the length of those ones are 1, and they are orthogonal because they are coming from the vector V1 and V2. And the theory tells you, Gram-Schmidt method tells you that those vectors are orthogonal. V1 and V2 is orthogonal. Once you do the normalization process, you will find U1, U2 orthonormal bases. You will get much more quicker when you're doing these calculations. Basically, it's a computational way. You don't have much thing to calculate. It takes time for me to explain it. That's the thing. And here, as I said, U1, U2, now you have an orthonormal basis in your hand, and you can check it in a corner. Always check it, your calculations, at least one of them or a couple of them, in order to be able to make sure that your computations is correct. Like U1, U2, if you multiply these two vectors as a dot product, and let's check it in a corner whether you got the 0. And it tells you that before you moving on, it will check your computation, especially when you're doing your assessment. It's an important step to go. Okay, you can do, as I said, you can do these calculations by using a matrix form as well, forming the matrix Q, U1, U2. But in that example, it is not preferable because your matrix have very strange members. I mean, you have 2 over 3. One of the column is this vector, another column is this vector, and you have root 41 and not really nice numbers. If you're doing by your hand, it will be difficult, but if you're doing with your computer, it's perfectly fine. So I'm going to use the first formula that I gave, the projection of the vector x on W vector space, W subspace. So it will be the just x and dot product with the orthonormal basis element as a linear combinations of the orthonormal basis element. So you have the dot product between x and u. So this was x given in the question. X is 381, right? This is the x is 381, and that's u1, 212, 1 over 9. 1 over 9 is coming from the 1 over 3 is coming, one of the 1 over 3 is coming from there as a coefficient of this vector in U1. Another 1 over 3 is coming from there's a coefficient of this vector. And this is why I have 1 over 9 here. And similarly here, I have multiplications of this coefficient twice, one in the coming from the inside the dot product and one in this vector. So this is why I have a square of this coefficient, so 941, and that's the dot product and that's the vector. If you compute this vector, you will find 522. This is the projection, this is the vector projected of x on this vector space W. Right. Okay, so you can think of that W as a plane spanned by this A1 and an A2. And then this vector, you have a vector x in your three-dimensional space, but not fully on the plane. And then the the vector x, the reflections of the vector x onto the plane gives you a vector in W. So this is the vector in W. And this is the trace, this is the projection of the vector x on the vector space as a vector. Okay, now we will do the same thing for the complement of the W. What is the vector which corresponds the projection of the vector into the complement space? So that is the W2, right? Every vector can be written as W1 plus W2 if you have inner vector space, all inner product spaces. We can do that. We can, and this is the subspace W, and the W2 vector is in the complement of W. Here is the W1 represents the projection of the vector on the plane W in your question, and W2 will be the projection of the vector on the complement space of the W. So basically, this is a very important equation, and this equation really saves a lot of time. It might be some tricky assessment questions related with this equation. Please learn this equation. This formula is an important formula. So basically, this part of the question asks us to calculate the W2, which is the projection of the vector on the complement space. So that is V minus W1. I'm just making the W2 is equal to V minus W1, taking this vector on the other side. That's all. So V is 381, and we calculate the W1, 522. That's W1. It gives us minus 261. So this is the vector projected to the complement space, to the orthogonal complement space of W, representing the vector V. Okay, next part of this question. What is the shortest distance from a point to W? From any point to W will be the shortest distance is always the projection, basically. The projection will be the shortest distance because from here to here, you need to go down with the angle 90 degrees, right? So this has a 90 degrees distance. So this distance is the shortest. But this distance is W2, right? This is the construction of the theory, the construction of the calculations that we've done. So the length of the W2, it will be giving you the shortest distance. W2, as you realize that the projection of V on the complement space, everything in around, so this plane is W, everything around it is the complement space. So W2 is in complement, V is in a complement. And W1 is in W, as I said that. Okay, the length of W2, well, this is W2. You calculate the length of W2, square root of square of this plus square of this plus square of this, which is 41. So that is the shortest distance of V on the plane W. And for the reflection formula, the part D asks the reflections of V on the plane with respect to the plane W. So basically you go down to the W, and then since W is your mirror plane, exactly the same distance you came down to the W, you need to further go ahead to the other direction to find the reflection point. So the reflection, I represented here as a T transformation, represented as the reflections of V with respect to the W plane. This distance and this distance should be exactly the same, and this point exactly this needs to be 90 degrees, this needs to be 90 degrees. So we would like to find out that this point is a reflected point of V with respect to the plane W. So with this distance W2, as we realize that it is the distance between V minus W1. So because you can think of this one as a vector addition as well. This plus this gives you W1 plus V minus W1 will give you V. This is also you can verify it with respect to the vector addition. So TV, this is the point that we would like to find out. TV minus W1 should be equal to V minus W1, but we need to put the minus here because they are in the opposite direction. This one goes up and this one goes down. So this is why I have minus here. So TV, it will be, when we are taking this one on the other side, will be just 2W1 minus V. This is just thinking about what is a reflection means with respect to plane W. This is coming from this thought. And we know that V is W1 plus W2. So TV will be, when we are putting the V as W1 plus W2, that will be W1 minus W2. Well, if you put this one here, you find TV is equal to W1 minus W2. So this one W1 and this one W2, then we calculate to TV as the vector 7 minus 4, 3. So that is the reflection vector. That is the point of the reflection of the V with respect to W. You can do it in another way. You can do it with respect to, in general, the reflection map is given by a formula, which is, let's say, R is a reflection formula, I is the identity matrix, and D is a dot product of the vector D and D, and D transpose is the matrix multiplication. So let's have a look what I mean by that. So D here is the W2, which is minus 2, 6, minus 1 in our case, right? So W2 is minus 2, 6, W1, which is this distance, this vector here. And that vector, that's the D vector. That's the D vector. And we can find as a reflection as identity minus, and looking at the dot product, this vector by itself, which is just 41, and multiplying D, that is D, and this is the D transpose. And multiplications of these two gives us a 3 by 3 matrices. Right? This times this is 4, this times this is minus 12, 2, minus 12, 36, 6 times minus 1 is 6, minus 1, 2 is 2, minus 1, 6 is minus 6, minus 1 is plus 1. So this one gives me that this matrix is a matrix multiplication, and this number is 2 over 41. And there's an identity here, and you can calculate the reflection matrix is as 1 over 41 and this reflection matrix. And this is the reflection as a linear transformation with respect to the W for a given D. Well, D in this case is a normal as well. So you can also do such things with the reflection map. So this is how you calculate a reflection transformation in general as an example. This is an extra bit for this question. It's just an exercise how to calculate reflection transformation because I had the example of it. That's all for this question. Thank you very much for listening through.